So this is the test review. So the first thing we're going to do is we're going to just take some sets and perform three operations, meaning negation or the complement, the union, and the intersection. So let's look at each one of those separately. So let's say I ask for the complement of C. So the complement of C is a set, and it's the set. And let's say A is the universal set. Actually, let's just say it's the universal set is that, and we don't even need set A for what I'm doing to demonstrate here. So that's the universal set, and so it's the letters from A to K, A, B, C, D, E, F, G, H, I, J, K. So the complement of a set is the elements that are in the universal set, but not in the set. So I have D, E, F, G. So the complement of D, E, F, G is the elements here that are not in there. So you can just go alphabetically if you want to. A, B, C. I don't include D, E, and F because those are in C. So this is everything that's in the universal set but not in C. So then you go D, E, F, G, and then go back here, H, I, J, K. So that's the complement of set C. The complement of set B would be A, C, E, G, I, J, K. Okay, so let's look at the intersection. So let's say we do the intersection of sets B and the complement of A. Actually, I don't have set A, so let's use the complement of C now. And we're going to actually do the complement of D, so we have to do the complement again. So in this case, to do this set operation, we need to have the complement of D because I don't have that written out. So first thing we do is the complement of D. So the complement of D is the elements that are in the universal set that are not in set D. So we see E, G, H, I, K. So which letters are in here but not in there? Well, we have A, B, C, D. E is in there, so I don't include that. F, G, H, I, J, K, and that's it. So that's the complement of D. The elements that are in the universal set but not in set D. Okay, so then if we do this operation, you can look back and forth between these two sets, or you could write it out. I'm just going to write it out so that it's easier to see. So I'm doing that intersection with the complement of D. So that's A, B, C, D, F, K. Well, the intersection is the set. So the result of this operation is a set, and it's the set that contains the elements that are in both A and B, or this set and that set. So we look, we see A's in this set but not in this one. We see the B's in both sets, so we're at 10. D is also in both sets. F is in both sets. H is in this one but not in that one. So we're actually done. There's three elements that are common to both sets: B, D, and F. So that's what the intersection is, and we're looking for that. And the final thing might be more than one thing. So if I do, let's say, C union B union C intersect D. So again, I need to do this first. Don't try to do everything at once. C intersect D is a set. And so I'm looking for the intersection. So I'm looking for the terms that are in both sets. So I see that I have E in both sets, and I have G in both sets. So the intersection is going to be the set of the elements E and G. Notice I have D here, but I don't have D there. I do have E both places. F I have here, but not there. And G, I have that. Okay, so that's the intersection. So if I want to find this, I could write out B. Set B is B, D, F, H, union this result, which is E, comma, G. And remember, the union is when you have the union of two sets, you create a third set. And it's the elements that are in either this set or that set. So we just kind of go along and we go back before, and we see we have B here but not there, so we write that down. We have D here but not there, so we write that down. We have E here. We have F there. We have G there. We have H there. If we had any cases where we had a duplicate, which doesn't happen in this case, then we would list it one time. So if I had G here and G here, we just list it one time. So intersections usually are smaller sets than the original sets, whereas the unions are usually bigger than the original sets. Well, they have to be either equal or smaller in size. These have to always be equal or bigger in size. Okay. Now, one problem is looking at a Venn diagram where we have these numbers representing the number of elements in these different locations within the three sets, sets A, B, and C. And what I'm going to ask you is I'm asking for the number of elements represented by this statement. So usually we have, A, B, and C, or A, B, and A intersect B with intersect not C. We're not going to do unions because that gets a little more complicated. So when you have an intersection of all three sets, that's this area. That's where all three sets overlap. So if I asked you what's the number of elements in this intersection, the answer would be 2. It's the one right in the middle. Now the other possibilities are we could have 2 letters and a complement. And you can have these in any order when it's intersection. So it could be a complement first, it could be whatever. Usually if you have one complement and 2 regular sets, you place this one last, you might rearrange it. So this one's at the end. So it's already in the right order right now. So what we do is we say the first operation, B intersects C, is this football. Intersections are footballs. And then the intersection with the complement is the same as subtracting. So here we have B intersects C. Subtracting A means getting rid of that. So if I said what is the number of elements in this, you would say 1 because it ends up being this area here. So these 3 parts, which look the same, are an intersection of 2 sets, subtracting out the third set. Now the third case is you have 2 complements and a set. Well, in this case we are going to rearrange them again. And remember, intersecting the complement is the same as subtracting. So I'm going to change that to a subtraction. So if we take set A and we subtract out, we take set B and we subtract out set A and we subtract out set C, what's left is this little corner part. So the number of elements associated with this is 9. This number would be A minus B minus C. This one would be C minus A minus B. So now we have this, which is the intersection of all of them. This one here is the intersection of A and B minus C. This one here would be the intersection of A and C minus B, and this one would be the intersection of B and C minus A. And then these 4 here are A minus B minus C. This one would be B minus A minus C, and this one would be C minus A minus B. And then the final one is the intersection of all of them, of all of the complements, and I didn't write a number out here, so I'm just going to write it out here. So when you have complement A intersect complement B intersect complement C, it's this number right there. So the number of elements in the intersection of the complements is 5. So it'll be one of those 4. So if you understand all those, you'll be in good shape. Okay. Now we have one of these problems where you need to fill it in based on the given numbers associated. So we go one way here, we go the other way there. And you usually work it in this order, but for your case, they're not going to be in this order. You're going to have to decide. You're going to have to figure out what order. It's the same order, they're just not listed in this order. So I might have this one listed here, moved around. But you always start with the intersection of all of them. The intersection of sets A, B, and C is this little thing in the middle, so that's 7. Then you go to the intersection of 2 sets instead of all 3 sets. So this one is the intersection of A and C. Here's set A, here's set C. So the intersection is this football. So it says 12 have to be in the football. Well, I've already got 7 in the football. So to make a total of 12, I'm going to make that one 5. Don't stick 12 in there. Okay? Don't stick 12 in there. Take 12 and subtract what's here already in the middle to get 12. Okay, next one is A intersect B, which is this football. Again, total in the football is 15. I've already got 7 accounted for, so 15 minus 7 is 8. Don't put 15 here, okay? These two added up should equal 15. So then we have B intersects C, which is this football. We have a total in there of 17. So I've already got 7. So this is going to be 10. 17 minus 7 is 10. Don't put 17 there. Okay, so that's good. Now I've given you the number of elements in set A. So that's all of the things that are in the total circle A, and I've already got 3 parts. I just need to figure out what's in this little wedge thing. So what I've got, if I have total of 40, so this is where I might start writing things down. So I'm going to have a total of 40 in A, and I'm going to subtract what I've already got and take into account, which is 8 plus 7 plus 5, which is 20. So that means that the part out here I haven't filled in is 20. Don't just put 40 in there, okay? 40 is the total. Okay, set B, 35 is the sum of all these 4 pieces. I know I have 3 of the pieces. So I'm going to take 35 and I'm going to subtract the sum of those ones that are already on there. So that's 35 minus 8 plus 7 is 15. 15 plus 10 is 25. So that equals 10. There it goes right there. Now, if I did, the number of elements in C, I could do the same thing, but I'm going to add something a little bit different. And so I give you the number of elements in A union C. Well, A union C is everything that's in A plus everything that's in B. So you can see that I already have what is in A, and I don't double count these, so I'm just going to go this one plus this one plus this one plus this one plus that one, which is in C but not in A, plus this one has to equal 46. So if I take 46 and I subtract the sum of these, so I'll have 20 plus 8 plus 7 plus 5. So that's those, this one, that one, that one, that one, plus that one. That's 20 then you've got 28, 35, 40. So you get 46 minus 40 is 6. So 6 go in there. I've got that. And then I've got the number of elements that are in the complement of A. So the complement of A is going to be everything that's not in A. So I don't want to include these. But this one's not in A, this one's not in A, this one's not in A, and also this is not in A. So the final one, I would take 39 and I'd subtract the things that are not in A that I've already figured out, which is 10 plus 10 plus 6, which is 39 minus 26, which is 13. So that's 13. And now you have everything. So if I said what the number of elements in A, not A intersect, not B intersect, not C, they don't give that, but that would be 13. That's this thing out here. If I wanted to know what is the number of elements in A union B, I had A union C here, A union B, I'd say, okay, A union B would be equal to this plus that plus that plus that plus that plus that. Everything that's in A and also this extra stuff that's in B. So that would be 20 plus 8 plus 7 plus 5 plus 10 plus 10, which is 20, 35, 40, 50, 60. Okay, they're going to ask, we're going to ask about whether certain statements are equivalent. And they're going to be on the order of something like this. Will involve P and Q, or not P and Q, not Q, ands, ors, if thens, all the logic things that we know how to do. So what you have to do is you have to construct truth tables for both of these and then look at the final result. Both of these are going to require a 5 by 5 table. So what I'm going to do is I'm going to move this down here so I can put another table below. So let me add another 5 by 5 table. Why is it 5 by 5? Because I have two statements, P and Q. So you take 2 to the second power, that's 4, plus 1 is 5. So that gives you the number of rows. The number of columns is the two letters, P and Q, PQ, the logic statement, P if then statement, negation of Q. Same down here. Got P and Q, 2 to the second power is 4, plus 1 is 5. That gives you the number of rows. PQ, not P or Q. So let's fill out the truth tables. Okay, so true, true, false, false, true, false, true, false. So those are all the different combinations of trues and falses. We have a P column, so we just copy the P column down as far as the truth values are concerned. We have the negation of Q, so we go to the Q column and change trues to falses, falses to trues, trues to falses, falses to trues. And then we use finally we use the rule for if-then statement. The if-then statement is only false if the first one is true and the second one is false. So this is the only one that's false, and these all are true. Okay, do the same thing down here. True, true, false, false, true, false, true, false. Here I have the negation of P, so I take the P column and I change true, true, false, false to false, false, true, true. Q, I just copy, so I get true, false, true, false. Then I use the OR operator. The OR operator says it's only true if they're both false. I mean, they're only false if they're both false. So I see I only have one case where they're both false. So this is false. All the rest are true. So now I compare this column with that column. So you've got false, true, 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 false, true, true. So obviously they're not the same. So since the results of the truth table are not the same, then the statements are not equivalent. If they ended up being the same, you would write the same thing, except since the results of the truth table are the same, then the statements are equivalent. So it's one or the other. They match up. If they match up, then they are equivalent. If they don't match up, then they're not equivalent. Okay, so then we do some more complicated truth tables. Remember, the number of rows in the truth table are either going to be 5, 9, 17, or 33. 2 squared plus 1, 2 to the third power plus 1, 2 to the fourth power plus 1, 2 to the fifth power plus 1. And in reality, to be honest, it's going to be one of these two, because otherwise it's just too big. So those are the number of rows. And in this case we have P, Q, and R, so it's going to be 9. We're going to need 9 rows. And then we need the number of columns. So okay, so the number of columns, we're going to have 3 columns for the 3 letters, and then we need to break this logic statement up. So that's 1, 2, 3, 4, 5. So that's going to be 8. So 3 plus 5 is 8. So we have 9 rows, 8 columns. So let's go ahead and make that table up. So let's see, 9 rows, 8 columns. So there we go. That's the right size. Okay. So then we write in P, Q, R. Negation of R, and if P, then not Q. So we fill these out. They should never be more than 8 or 9. Well, this should be never more than 8. You may use more than 8. Something wrong, because I've told you already that we're only going to do one of these two. We're not going to do any bigger. So if you do more than 8, you haven't been listening to my review. So it should be. Okay, so remember we do 4 trues, 4 falses, 2 trues, 2 falses. Then we alternate. So those are all possible combinations. Trues and falses. Okay, next thing we do, fill in the columns with the letters or the negation. So here I have the negation of R. Here I have R. So I just write the same pattern, but start with the opposite truth value. So all the trues become falses, all the falses become trues. Here we have P, so we just copy directly down. Again, this is not something you should mess up. And then Q is, there's the negation of Q, so I have to change these truth values. So I switch it around. So instead of true, true, false, false, it's false, false, true, true. Then I repeat the pattern. Okay, so I'm almost done. you always do what's in parentheses first. So I'm going to compare these two columns. Use the rule for if-then. The if-then statement is false only if the first statement is true and the second statement is false. So I'm going to put that in red. So that's going to be true, false is false. True, false is false. True, true. Well, yeah, I've been saying to go through and do all the false ones first, and then so I get true, 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 true. Okay, the rest of them are false. I mean, they're true, because only the first two have true, then false. Okay. Then once I have this column, then I'm going to compare it with what's on the other side of the and statement. So the and statement is true only if both of them are true. So I'm going to compare this column, put my finger here, put the second finger there, just move my fingers down looking for the case where I have two trues. So I have that here and I have that there. And then I have another one here, true, true, so I put that there. And true, true, so I have three. Three, they're both trues. And then the rest are false. And that's all you have to do. You don't have to answer any questions about it at this point. Just put a little arrow here to show that you realize that that's the last thing that you do. Okay. Then I have one that's a little more complicated. It still has P, Q, and R, so it's still going to be 9 rows. So we're going to say 9 rows. Number of columns, well, we have 3 for P, Q, and R, plus how many we need for this logic statement. So that's 1, 2, 3, 4, 5, 6, 7. 7. So that equals 10 columns. Some of the truth tables may be just exactly the right size, and some may be a little bit big, so don't make any assumptions. Okay, so I want to make my table, which is 10 columns. So I'm going to make 5 columns by 5 rows. Squish this down so I can fit it all. So there's my 10 columns. And we'll overlap one here so we get 9 rows. Okay, so there's my table. So now we've filled it out. P, Q, R. Just do this in alphabetical order. Just to make it easier. Okay, and then we have the logic statement. So we have Q, or, not R. And then the if-then statement, R, if-then, not P. Okay, so I can drag that down now that I have it all written out. Same as last time. True, true, true. False, false, false. True, true. False, false. True, true. False, false. And alternate. True, false, true, false, true, false, true, false. Okay, now fill these 3 columns in. So we have Q, so that's just a direct copy. We have the negation of R, so we go to column R, see the pattern, switch the pattern to the opposite. Okay, go to the next column, R, so that's just a direct copy. Now while I'm doing this, you know, if you just write down these examples on your cheat sheet and you don't understand how I did it, you're not going to be able to figure it out. You know, if you look at the truth table, you're like, I don't remember how I did it. So you need to either know what you're doing or explain what you did so that when you get there, you're not going to completely screw up. So don't just think, oh, I'll just copy this down and then I can use it directly. It's not that simple. Okay, and the negation of P is the opposite. Okay. So because we have two sides, we're going to do this on the left-hand side and do this on the right-hand side. So it doesn't matter which one we do first. So let's do this one. This is the OR statement. An OR statement is false only if they're both false. So we put a finger here and just follow them down. Look for the cases where we have two falses. And that's the two cases, two falses. And therefore, we have all the rest true. OR statements always have a lot more trues than falses. And we do the thing over here, the if-then statement. So again, the if-then statement is only true, only false, if the first one is true and the second one is false. So our first case here is that true and false. So that is false. True and false. That's false. All the other ones are the other combinations. So we've got the two that are the kind of the exception, and then we have all the other ones we can just make trues. And then finally, these are the truth values to the right-hand side of this. These are the truth values to the left-hand side. So we're going to compare these two columns and then apply the rule for the statement that's between them. So again, this is an if-then statement. So an if-then statement is only false if the first one is true and the second one is false. So again, we have the first one is false. So we're just going back and forth, looking for true, then false. And we see that that was the only case, the first case. So all the other ones, they're not just not true, false, but all the other three combinations are true. So there you go. You're done. Bingo. Now I want you to be able to show what area in the Venn diagram is represented by the operation shown above. So we've used the same skill, just in a different way before. So the way we do this is we say, okay, let's do the intersections of two sets. If we have two sets that are intersecting, not the complement, we do the intersections, the two sets first. So if we call this A and we call this B, we call this C, A intersect B is this area right there. And then intersect the complement of C is the same as subtracting out what part of A intersect B is also in C. So you get this a little bit here. This is A intersect B intersect not C. This one would be A intersect C not B. We've already talked about that. We have the other case where you have two complements and just a regular one, and you could rearrange those. So the way you do these is you would, again, we'd have to label them so we know which circle represents which set. In this case, you start out with C. So you don't start out with an intersection. You start out with C, and then you erase what's in A and you erase what's in B, and that's what you're left with. So that this is equivalent to that. This is all of C subtract A and B. And in this case, B union C. Well, what is B union C? So B is this, and C is that, and the union means you count both of them. Whereas the intersection would have been this area. The union is both circles. So that's the first thing. And then you subtract A, which means you erase the stuff that's in A. This also would be the equivalent to B union C intersect the complement of A. So that would be another way of writing it. Okay, now here's one of these survey questions that you have to generate the Venn diagram and answer some questions. So let me see if I can make this a little bit bigger so we can see this. Okay, so you're going to be given something like this, and then you have to fill in the Venn diagram. So I've surveyed, I just made this up, surveyed about men's sports preferences. There were 112 men surveyed. So we have all of this data. And basically you want to do it in order where you always start with all three. Let me put that afterwards. So first look for the one that's all three. Then you look for intersections. So intersections are ands. So this, you do this second and this third. So about basketball and golf, football and golf. You can do either one in whatever order you want to do. Now you've got this football or golf, and that's usually later because you need more information to solve that. You might have likes two sports but doesn't like golf. Well, that would be like B intersect F intersect G complement. So let's just look at it. We just did it in the second go. So if you have B intersect F subtract G, that would put the number right there. Okay. So that looks like, that'll give you one particular area. You don't even have to do any math for that. And then you would use probably these. So this one would be fourth. And then you would do these two, probably. And then this OR is probably going to be last, well, next to last. And then you'd have to use the men surveyed to get the number out here. So let's see what happens. 10 liked all three sports. So this is where they like everything. Second was and 19 liked football and golf. So this is the football intersect with golf. We already have 10. So to get 19, we have to put 9 right there. 19 like football and golf. So let's mark these off as we get them done. Okay, the third one was, third one, 25 like basketball and golf. So here's basketball, here's golf, this is the intersection. I already have 10, and it says 25. So what plus 10 equals 25? 15. Okay, so I got that taken care of. So that was 3. 4 was 9 like basketball and football, but didn't like golf. So this football here, in a Venn diagram standpoint, is basketball and football. But by saying didn't like golf, you get rid of that, which means that 9 fit right in there. And you can see I've got 3 out of 4 here, I've got 3 out of 4 there, and I've got 3 out of 4 there. So I can use these, the ones for just a particular sport. So let's start with football. So we had 63 like football, which is this one. But I've already taken into account these other 3 parts of the circle. So that's 63 minus 28. 63 minus 28 is 35. So 35 goes right here. So if I had this plus this plus this plus that, that gives me everybody likes football. Okay, so did that one. 49 like basketball. So we take 49, subtract the 3 that I've already got to take into account that are already in B. So it's going to be 15 plus 10 plus 9, which is 49 minus 34. So 15 plus 10 is 25. 25 plus 9 is 34. 49 minus 34 is 15. So this is 15 in the basketball. So that was number 6. Liked football or golf. Well, here's football. Here's golf. The only part that I don't have a number in is right here. So I take the 83 that like football or golf, and I subtract the sum of all these 5 things that are either in F or. So I have, let's start out here, we have 35. Let's just do F first. 35 plus 9 plus 10 plus 9. That should add up to be whatever we got up there. And but we also have one more term, because we got these 4, but there's also this one there, which is 15. So you add 15 to that, and so you get 83 minus the sum of those things, which is 78. So the 78, subtract 78 from 83, and you get 5. So this is 5. And we're almost done. We don't have what's outside there. So we had 112 men surveyed. And we already have all these other ones taken into account. So we add all those up. There's going to be 1, 2, 3, 4, 5, 6, 7. So we add 7 numbers. 15 plus 9 plus 35. So that's 3. 15 plus 10 plus 9. 15 plus 10 plus 9. And then 5. So we get 112 minus whatever the sum of those things is. 15 plus 9 plus 35 plus 15 plus 10 plus 9 plus 5. I forgot a parenthesis there. We get 98. So 112 minus 98 is 14. So the 14 that I don't like any of those sports. I know it's strange that that would happen, but so once you got that filled out, you got the first part. Then it says, after filling the Venn diagram out, answer the following 2 questions. How many men don't like any of the sports? Well, that's 14. Let's put that answer in. 14. How many men like football and golf but not basketball? So let's go back up here. Football. Here's football. Here's golf. This is football and golf. But when it says but not basketball, you take that out of there. So you're going to have football and golf, but not basketball, leaves you with 9. And then you're done. Okay, we talked about the Cartesian product, and what that is if you have 2 sets, A and B, and you do the Cartesian product, that's going to end up being a set of Cartesian pairs. And the number of Cartesian pairs is dependent upon the number of elements that are in the original set. So let's say I have A, C, D for set A. They don't have to be numbers. It might be numbers. We're just going to use letters here. And they don't have to be different. You can have C and E. So the Cartesian product, because we have 3 in this one and we have 2 in that one, 3 times 2 is 6. So we need 6 pairs for the result. So it's a set, so make sure you put the set sign. And the pair is you're going to use the first element in set A with the first and then the second elements in set B. So you're going to have A, comma, C, A, comma, C, and A, comma, E. Then you go to the next letter. So the first, A is the first thing here, so it's always going to be the first letter. So you take the letter C, you go to the first letter here, which is also the letter C. Then you have C and E. Another comma, 2 more, change the first to a D, so you get D, comma, C, and D, comma, E. So there's the 6. Actually, these are, you have to use parentheses there. No, so let's fix that. So the pairs have parentheses. And you end it with a squiggly. So I'm just doing a Cartesian product B. If you change the order, then you'd use these for the first number in the set. Okay, there's a couple of questions about whether sets are equal or not, and we had some of this for homework. So if I said is set A, B equal to set BA? And the answer would be yes, because they have the same elements. That's all that's important. The order is not important for sets. Whereas if I said 2 comma 5, is that equal to 5 comma 2, which these are Cartesian pairs, not sets. So in Cartesian pairs, the order is important. So this we'd say they are equal. This is true. This is not equal, or false. I guess you might have a true or false. It's a true or false. So this is true because they are equal. Here this is false because they're not equal. And the third case would be if you have a set of Cartesian pairs. So let's say you have 2 comma 3, 3 comma 5, 3 comma 7. Okay, so those are your Cartesian set of Cartesian pairs. So you'd have to have the same Cartesian pairs. You couldn't change the order. So if I were to do 3 comma 2, it's the same numbers, but it's a different order. So those are different things. When they would be equal is if I repeated this exactly the same, or if I did the same Cartesian pairs in the same order in terms of the Cartesian pairs, but I changed the order of the Cartesian pairs. So I've got 3 comma 5, and I've got 2 comma 3, and I've got 3 comma 7. And this would be true. So this one was true. This one's false. So in this case, they're true because the order of the listing of the Cartesian pairs is not important when it comes to sets, but Cartesian direction is. Okay. I'm not going to do an example. You can go back and look at your homework, but there was a case where you were given 2 statements, and you were given some symbolic logic, and then you had to convert the symbolic logic into words involving the statements that you were given. We did that one way. We also started with the words, and we converted that into symbolic logic. So it's let me see if I can find it. What page it is? Those should be easy, and you shouldn't. I'm not going to do an example just because I. Okay, so that would be well, I know we did some. Oh, it's because I'm looking in the wrong chapter. So I think it's section 3.1. Yeah, so if you look at problems 39 through 48, that's where we take symbolic logic and make it into words. And then 49 through 54, we take words and create symbolic logic. So that's, you're going to see a few of those. Those aren't going to be worth as much because that's hard. Okay, there's going to be one problem which asks you to determine whether something is a statement or not. You go to the homework. If you look at problems, this is section 3.1. Problems 1 through 14. So 1 through 14, pages 88, 89. And negations, that's same section, 23 through 32. So the key thing to remember here and to review is some of them just say a statement, and they're easy, just put not. or something like that. But if you see words like all, some, every, what else have we got here? Yeah, so 23 and 24 are the ones that are the easy ones. Then you've got these other ones, 25 through 31, which use more broad terms, so you've just got to be careful about how you write the negation of those. And I guess one thing I told you, I guess you could use, you always say it is not the case. That always works. And that's it, pretty sure. So let's kind of go back and review what we've reviewed. So, use set operations, negation, intersection, union. Make sure you can write the sets out. Understand which areas are represented by these set operations, and then be able to identify on the graph how many elements. Just look at the number. And given this information, generate the chart. Prove or disprove that two statements are equivalent by looking at the final truth values. Be able to do truth tables. Again, given, it's really just like the previous one, except you're just coloring in the area represented by these set operations, intersections. Doing a survey question. Taking the survey information, filling out the Venn diagram, and then answering some additional questions. And then just some simple things that we kind of loose things that we talked about. Okay, so that's it.